Good morning, thank you. This is a volume-based merge heuristics for disjunctive numeric domains. I'm Andrew Ruef. This was also done with Arlen Cox and Kesha Haitala. They're both here with me, so if anyone asks me any strange or confusing questions, I can defer to them, which makes me feel very good. So this is about where we're going to go with this talk in 4 different parts. So our motivation is we'd like to analyze programs that have strange features in them, like branches and numeric properties, and we like to prove different things about the numeric properties that the programs use. So imagine you have some program that looks like this, where there are 3 different branches with 2 different variables, and we use convex polyhedra to abstract the representation of the numerics x and y, and there are these 3 different cases, A, B, and C, where different things are happening to each one of these numerics. And then finally, at the end, we have a point where all of these values will come together, and we have the option to join them. So what happens when we do that inside of this program where x is bounded by -2 or 1 or 0, and y is also has its own set of bounds. So if we represent what this looks like on sort of the xy plane, we have sort of a region A, a region B, and a region C, and we can sort of represent graphically what the pre-join space looks like before we bring them all together. So if we bring them all together, we lose some information. And that information is sort of in this negative space between A and C. So if after this point we were to ask and we wanted to try to prove some property that relied on the absence of that information, we would have a problem, and our tool would over-approximate soundly and say, oh, it's possible for that to be the case, but looking at the structure of the program, you would say, oh, no, that's not the case. This would be a false alarm. So is there something we can do to soundly mitigate this and sort of regain some precision? Well, so what if we had these A and B objects and we kept them separate, and then when we were given the C object, we could say, well, I'm not going to join all of them together. I'm going to try to put C with either A or with B, and either choice is sound, but one choice would be more precise than another. So which C should it go with? Now, if we look at both of these options in sort of separate graphical planes, we can see that one encompasses the negative space that we want to avoid, and the other does not. So our question when we're managing this disjunctive domain is, if we have A and B joined with C, is that either A joins C or B joins C? So we said, well, what if we guide the decision of which one of these options to go with by computing an affinity score between C and B and C and A. And this score will tell us which one which A or B C should go with. And again, either way, this is a sound approximation, but one is more precise than the other. So the motivation behind this was our affinity score should try to minimize the precision that is lost. And so we should sort of wind up with the smaller disjoint objects. The score is going to be sort of a real value between 0 and 1 that describes which one represents the least loss of precision. So this is in the spirit of prior work that uses, and so this is a heuristic like other heuristics. It joins a list of heuristics that we can use to manage disjunctive abstract domains, such as using common hyperplanes or the Hausdorff distance. But in this case, we're sort of looking at semantically similar polytopes directly by looking at the volume. So we have 2 different notions of volume. One is the sort of real valued relaxation volume of the interior of the polytope, and then another is the count of integer points that are contained within the polytope. And our affinity scores are going to tell us either sort of what is the overlapping volume of the 2 polytopes as we join them. So let's look at what that is. So one option, so let's think about the intersection volume between A and B. So imagine we have these 2 rectangles, and our affinity score is going to be, well, what is the proportion of the polytope where the intersection, where we have the intersection over the union. So we have this example here. We have these 2 rectangles. We sort of slide them on top of each other. There's a volume of 4 that's contained in both, and then a large volume of 28 that's the union. And so this tells us, hey, there's some similarity. And you can imagine in your head like taking these 2 rectangles and sliding them around. If you remove them totally disjoint, the score will go to 0. And if you overlap them on top of each other, the score goes to 1. So then what this score would tell us is if there's lots of overlap, there's lots of similarity. So you probably will minimize precision loss by joining two objects that have a high precision, high affinity score. However, if you would say, oh, if there's no overlap, then there's no similarity, which is true, but that's not the only case. So imagine if you took the two rectangles and you slid them directly next to each other and you computed this score. So if you did that, you would wind up with a score of 0, which doesn't sound good, because if you join these two things, you won't lose any precision at all. So that doesn't, there's a case that you can identify where this heuristic doesn't work, which is not too surprising because it is a heuristic. So what if instead we develop a different heuristic where we measure the union volume over the whole volume? So if we go back to this case, suddenly we wind up with, hey, this is a precise score of 1, you can do this join, and then this is also in the spirit of other work that detects the presence of the ability to perform a precise join. So that sounds good. Now we have these two different heuristics. We're starting to get into territory where we could think, oh, I wonder what the trade-offs of using these in practice are. Well, we'll get to that. And if we go back to our previous example, we say, hey, so there's the case for this precise join. That sounds good. What if we go back to sliding these things around? We wind up with this negative space that tells us that there's some difference between them, which is also good. That was what we got from the first measure score. So now we have the second score, and that's nice. So let's consider the complexity of these different heuristics. So if we think about the overall complexity of computing the numerator and the denominator, if we're just looking at the intersection and the union, that complexity is polynomial. When we start to involve the whole, this becomes exponential. There are algorithms where we can precisely count the number of contained integer points. Those algorithms are exponential. So then we would say, oh, well, what if we want to, how do we want to compute this real relaxation volume of these objects A and B? So we could use a statistical approximation where we perform sampling inside of the interior regions of A and B, and then use the points that we generate inside of A and B to approximate their volume. The good news about that as an approximation is that its complexity is better than the algorithms available for exact counting. That's polynomial. So then you would say, well, this is good for the case where we're working with the intersection and the union, but what about the whole? That's still exponential. So we realized, oh, we're computing all of these points. Perhaps there's some way that we could exploit that to approximate computing the whole as well without having to pay the exponential cost of computing the whole. So then we can say that we can calculate this second row in polynomial time. And so what does that look like? Well, so we have our previous objects A and B. We have random points that we've sampled between A and B. And we would say, OK, let's choose a random point from A. Let's choose a random point from B. Let's cast a line segment between A and B. And let's calculate how much of the line segment is contained either in A or B alone, or outside of A and B, or inside of both A and B. So this gives us another score between 0 and 1 that we can use to judge the affinity of polytopes A and B, and then this works in our case where they're sort of sliding around, and it also works in this abutting case rather nicely as well. So when we were looking at this, part of our intuition was, oh, this is sort of like casting an approximate shadow of the hull. As you take more samples from inside of A and B and you draw more line segments between A and B, you wind up with this sort of hazy, cloudy shadow of the hull of A and B. Now, this there are a few downsides to this in terms of it's difficult to view this as a sort of uniform sampling of the hull of A and B, because you'll wind up with the shadow denser towards the centroid of the hull, but then much hazier and thinner towards the exterior portion of the hull. So it's not a perfect approximation or uniform approximation of the hull, but again, since this is a heuristic, if it works, it works. That sounds good. So this takes us naturally to the question of, does it work? So when we set out to evaluate our different heuristics, we had a few different research questions. So when we have this affinity score, how effective is the use of performing exact counting of the interior volume, using the approximate volume via statistical sampling, and then using line segments to approximate a shadow of the hull? Also after that, so we have this theoretical result about how our sampling approach is a polynomial of polynomial complexity, while our exact counting is of exponential complexity. So does that theoretical result predict what actual empirical evaluation would see if we were to run this on a reasonable sized benchmark? And also, in a similar spirit, do either of these techniques scale if we actually implement this and then run it on a benchmark? Will it work? The result to that one is probably obvious since I'm talking about it. I think if it was still running, I wouldn't be here. I wouldn't be able to be here. I'd be waiting for it to work. So when we implemented this, we built it on top of the CRAB LLVM analysis framework. To implement exact counting, we used the Barvinock library, which is open source and available. We implemented our own Markov chain Monte Carlo sampling algorithm to approximate the volume, and this also generates random points that are uniform random points for a particular object, and those points are then used for the segment-based Hull approximation as described before. And we evaluated this on, so the way that CRAB LLVM works is you compile your program, your C program, with the Clang front end. It turns into LLVM bitcode. LLVM gets turned into a CRAB intermediate representation. The CRAB abstract interpretation framework runs on that. We implement a disjunctive abstract domain that CRAB uses. That disjunctive abstract domain has its join decisions guided by our different affinity scores. So in addition to the sort of 5 different affinity scores that I was describing, where we were either using intersection or Hull volume, and then that in turn is parameterized by whether or not we're computing the count of contained integer points or the real relaxation Hull volume. We also, and then in addition to those 4 options, we have our line segments. We additionally implemented a null affinity, where there was everyone was equivalent to each other. So this essentially, if you have a disjunctive 3, that would always fill the first 2 and then join everything into the last one. That's sort of our base case. And then we also implemented the common hyperplanes approach as an affinity score to compare everything against. So now we have these 7 different analyzer configurations and our benchmark suite of code that we draw from svcomp and wset. And we take all of our different analyzer configurations and run them across every different benchmark program. Each analyzer generates invariants at every program point across the different programs. So then we take those invariants across all the different invariants produced for the same program point, and we ask, yikes, how often is it the case that an invariant generated from the first analyzer configuration is sort of subsumed by an invariant from the second, and then how often are they equal? So then this allows us to count up, oh, what is the precision gained by using a particular analyzer over another in terms of generating finer invariants. So when you compare them, you wind up with a cross table that looks sort of like this. So the way to read it is across the top, we have our first analyzer configuration, and across the side, we have our second analyzer configuration. And the value in each cell tells you this is when the first analyzer configuration was either finer than the second analyzer configuration or was equal to the second analyzer configuration. So the answer to one research question is counting the number of integer points and using that as a affinity score is fairly effective. When we compare it against the sort of null cases, we can see that, or the base cases, we see that it performs better than the null case and better than the common hyperplanes case, and also frequently better than the other cases that use real relaxation volume. So that was sort of kind of surprising, but we said, oh, well, the exact technique is performing an exact computation, so perhaps it would be better than the sampling-based approaches. And also, the sampling-based approaches that approximate the volume empirically don't perform as well. So we were kind of surprised by that because we said, oh, every time someone says I have this problem that has this theoretical difficulty to calculate exactly, I can approximate it, and then that will hopefully do you just a little bit worse, but much better on runtime. So when we tried that approach here, we saw sort of the opposite happen, and we were wondering, how is this possible? There are some engineering reasons in terms of implementing our implementation that could explain this, because our precision goes up with a number of points that you can sample from, and if the cost to sample an individual point goes down, you can only get fewer samples. So perhaps if we can make the constant cost of sampling a particular point lower, we can sample more points, and then our precision could go up. So either way, even if we have, so everything sort of, the three last columns are all on equal footing when it comes to the constant costs of sampling. So even then, we have this comparison between shadowing the hull approximately and using the relative intersection and hull volume computed approximately. And there isn't an advantage, it seems, to shadowing the hull over approximating the interior volume. Also sort of interest is that if we have this intersection volume and the hull volume, and we compute both of those scores using the integer points, they're exactly as precise always. So what this tells us is our worry earlier about, oh, what if I have these two rectangles and I abut them directly? The intersection volume case would lead me astray. In our benchmarks, that didn't happen, so perhaps that isn't a big concern, even though it is a theoretical failing of the heuristic. So you can also see this when we compare the runtime of all of these different approaches. So our two null cases have a very good runtime, and then we sort of get worse as we increase our use. So the other interesting thing was that, again, you would say, oh, well, surely this approximate technique would fare you better in terms of having a better average runtime because it doesn't come with an exponential cost. But again, on our benchmarks, these exponentially expensive algorithms had a better empirical running time than the polynomial implementation, which again could be because of implementation decisions. There's 15 years of implementation work inside of this lib-Barvanach thing, and about, if I'm being very generous, 1 year of implementation work in our sampling-based approach. So that could explain it. But the other interesting, so sometimes and there's some perhaps room for optimism in terms of those engineering decisions getting us within equivalence or maybe even better than the exact techniques, because in the worst case, the max column, one of the interior methods takes 900 seconds, while another of the counting methods takes 800 seconds. So hey, maybe we could make it faster by 2 minutes in that worst case, then maybe all of those numbers would get better. So in conclusion, and so for discussion, again, this was pretty surprising. So one example of the precision engineering involved in sampling is we had to make use of some numeric data type to represent interior points. And initially we thought, oh, we'll use doubles. That will be fine. So one complexity there is that there's a lot of literature in the sort of numerical mathematical community about approximating the volume of these polytopes. And those make, that literature makes the objects that they work with are very different from the objects that the analyzers work with. So we would cut all of the objects at the maximum machine integer size. So we would add constraints that would say, oh, even if something is potentially unbounded, we're going to sort of box everything off at 2 to the 61, 2 to the 63, sorry. And funny things happen with doubles at those extremes. So the way a lot of these algorithms work is they'll say, oh, go in some direction until you can't, and then pick another random direction, and then go over there. And so they'll sort of shoot around the interior of the polytope until you run out of time to sample stuff, and then the points that you get from that random walk on the interior become your approximation. So you could wind up just sort of stepping ever so slightly outside at the extremes due to double imprecision, and then the algorithm doesn't work anymore, and you sort of shoot around into infinity for forever. So in response to this, we started using GMP rationals, which are much slower. So you might say, oh, well, that surely explains the difference between your running time and the exact technique's running time, but it doesn't, because the exact technique also uses GMP rationals, but because they have all of this extra experience in managing this, they have lots of different aggressive memoization and caching routines ahead of their use of GMP rationals, which we don't, so maybe there are different engineering decisions that would help. But either way, we were excited and surprised to say, hey, this exact counting mechanism works. It seems to be effective as a heuristic for measuring affinity between different polytopes, and you should use it when you manage disjunctions today. Any questions?
We have time for a question or two. as far as I understand, you compare the result of the different approach qualitatively. Is it better or equal? The result is better or strictly included or equal. But couldn't you use the same machinery to get a quantitative comparison between the volume of
I see.
of the results?
Yes, yes. We had that thought. Well, yes, that is a. I think the answer is yes. I'd be interested in running that. I think what we were so when we started designing the evaluation, we thought, well, what is something that we could interpret, and then maybe yes. So maybe the thing to do is to sort of continue to present the data in the form. Maybe okay. So maybe this is an open question. We were wondering, oh, well, we could present the data as how often are these two proportionally less than or equal to each other. We could continue to do that, but instead we could replace this notion of subsumption with how often is the volume of one less than the volume of the other, and yeah, that. Yeah.
Are there more questions? Let me please ask you then one more question. You were talking lots about using this counting of exact counting. So which methods that were you using or which tool? Maybe you mentioned, but I
Oh, sorry. Yes, that was the Barvanok algorithm implemented in the libbarvanok library.
Mm-hmm. Okay, thank you. Okay, so let's thank speaker then once again.